In this question, we've got 4 elements: beryllium, boron, carbon, and nitrogen, and we're provided with the values for their first ionization energy in this table. The first question asks us which element's first ionization energy is an exception to the expected periodic trend. So first, let's go and have a look at our periodic table and figure out what we think should be happening based on what we've learned so far. So let's just find those elements. Beryllium is here, boron is here, carbon is here, and nitrogen is here. So we can see that all of our elements are in period 2, which means they all have the same number of energy levels, but we have increasing group number and therefore increasing effective nuclear charge as we go through our list. So I'm just going to label that on here. So because we've got increasing effective nuclear charge, we're also going to have increasing Coulombic force of attraction between the valence electrons and the nucleus as we go from beryllium to nitrogen. Now the question's asking about first ionization energy. Remember, that's the energy required to remove an electron. And the greater the force between the electrons and the nucleus, the more energy we're going to need in order to remove an electron. So because beryllium has the least force, we expect it to have the least energy required to remove an electron. And nitrogen has the most force, we're expecting it to have the most energy required in order to remove an electron. So we're expecting the trend to be that as we go from beryllium to nitrogen, we are increasing the ionization energy. That's what we expect to see. So let's have a look at our numbers now. As we go from beryllium to boron, we actually we subtract about 100 there. As we go from boron to carbon, we add about 300 there. And then as we go from carbon to nitrogen, we add about another 300 there to our first ionization energy. So which element has a first ionization energy that's an exception to the periodic trend? Well, boron, we'd expect to have a greater energy than beryllium, but it has a lower energy. So boron is our exception to the periodic trend. So the next question is, what causes this element's first ionization energy to be an exception to the expected trend? So to think about this, we're actually going to write out our electron configuration for each of these. So beryllium has 4 electrons, so let's write its electron configuration here. The first 2 electrons are going to go in the 1s subshell, and then the next 2 electrons are going to go in the 2s subshell. So 1s2, 2s2. That's our electron configuration for beryllium. What about boron? Boron has 5 electrons. So the first 2 are going in the 1s subshell. The next 2 are going in the 2s subshell. Remember, s subshells can only fit 2 electrons. So this one's then going to go into the p subshell, 2p1. Then we continue going. We've got 1s2, 2s2, 2p2 for carbon, which has 6 electrons in total. Nitrogen is going to be 1s2, 2s2, 2p3, since that has 7 electrons in total. Okay, so boron was the one that had an exception to the trend. And if we look at what's going on here, when we go from beryllium to boron, we're starting a new subshell. Or a new sub-energy level. So we were filling 2s, and then we start filling 2p. So we have a single electron added into the 2p subshell, and we have a pair of electrons in the 2s subshell, and that's actually going to experience some repulsion from the 2s subshell, the electrons within there. So we're going to experience repulsion between the lone 2p electron, because there's only one of them, and the 2s electrons. And that repulsion actually means it's a little bit easier to remove that electron than we might expect, and therefore that the ionization energy is a bit smaller than we might expect. And we actually see a similar trend if we were to look further, if we were to look at the next atom or element, which would be oxygen. Oxygen has a electron configuration of 1s2, 2s2, 2p4. And according to our periodic trends, we'd expect it to have a greater first ionization energy than nitrogen. But actually the value that we get is slightly smaller than nitrogen. So oxygen is another element that doesn't follow our trend. And when we think about what's actually going on here, if we visualize our 2p subshell in nitrogen, it's got 3 orbitals, which can each hold 2 electrons, and it's got 3 electrons in there. So each electron will be its own orbital within the 2p subshell, according to Hund's rule, which says that electrons don't pair up unless they have to. Now, when we add in that 4th electron, it has to go in a pair because there's no empty orbitals available in that 2p subshell. And because it's paired, it actually experiences repulsion from the electron that it's paired with. And so it actually has a lower ionization energy than we might expect, and it's a little bit easier to remove that electron that was added than we might expect according to our periodic trends.